This grid is the foundation for a PvP sword-fighting action game that I recently started working on. In this video, I'll share how I built and optimized this procedural hex grid using JavaScript and Blender. You might find some ideas to use in your own projects. There's also an interactive demo for you to check out below. But first, why a hex grid for a fast-paced action game? The short answer is physics. When I came across the famous Red Blob Games article on hexagonal grids, which in my view is the best resource on the internet for this topic, I had a few ideas on how they might be a great way to simplify combat interactions, specifically for movement and hitboxes, in addition to making it easier for my game simulation to be deterministic, so that I can implement replays. And it was actually Uber's H3 global grid system that introduced me to the concept, rather than game development, which I'm actually quite new to. As an aside, hex tiling a globe isn't possible without the help of some pentagons, but that's a little off topic. When I was playing with geospatial data, I really liked the idea of multi-resolution grids. Notice that when you zoom out from tiled hex rings, you roughly get a hexagon. And unlike tiling a globe, our game map is flat, and we don't have to deal with shape distortion. Now, squares tile perfectly into squares, but aren't ideal for hitboxes, because they're sharp. On the other hand, hexagons nicely approximate circles, so you don't end up with these corners that result in awkward hitboxes for players, and you can design them in more organic shapes for abilities, which means that you can do collision detection without running a physics engine, leaving more room in the performance budget for, in my case, animation. And that kind of optimization matters when your game is targeting the browser. Welcome. This is episode 1 of my devlog series on making a game incrementally, where you can playtest every step of development. Subscribe to get the next episode, and now let's get into the code. This is an empty 3D scene in the browser. To make our grid, we'll need to render a hexagon, generate grid cell positions, then use instancing to render copies of that hexagon in those positions in a performant way. But before all that, we need to set up a new project. I'm using JavaScript with Three.js. It's an open source library for managing 3D scene graphs, originally created by Mr. Doob, also known as Ricardo Cabello, with contributions from many great people. Their recent work on WebGPU is what makes my game idea possible in the first place. If you're curious about the topic, check out the videos I've linked in the description. Anyways, as you probably know, the JavaScript ecosystem has endless ways to set up projects, and countless library choices. For example, there are other great 3D libraries like Babylon.js. In my case, I chose Three.js because that's what I happen to know. I learned it through Bruno Simon's excellent course, Three.js Journey, that also taught me about shaders and a little bit of Blender. I'm using Vite to set up TypeScript with React, and installed React 3 Fiber, which lets you use React to render Three.js. It's an excellent library maintained by a developer collective created by Paul Henschel. They also have a library called Dry, which has many useful helpers for things like controls and performance monitoring, in addition to reusable components for all kinds of features that save you a lot of time that you no longer have to spend on manual configuration. The catch is that you have to be pretty familiar with React and Three.js to be productive with React 3 Fiber. My point in telling you all this is that even if you're working on your own project, you should use whatever you like or whatever you're familiar with. You don't have to do things the way I am because the underlying concepts are exactly the same. And if you don't have any particular preferences, Vite and Three.js are a great place to start. First, to render a single hexagon, we need to create a mesh using a geometry and a material. For the geometry, we create a circle with 6 sides. Yes. And for the material, I'm using a basic one that doesn't require or react to any lighting. Next, get the grid points by referencing the cube ring and cube spiral functions from the Red Blob Games article, and convert the cube coordinates back to Cartesian. Now, if the number of hexagons we want to render is small, we could just render each one as its own individual hexagon mesh as we defined previously. But beyond a couple hundred hexagons, the FPS starts to drop, even if we use a single geometry and material shared between each individual hexagon mesh. Instead, we can use instancing to render large numbers of hexagons, but there's a small catch. The built-in helpers for instancing have some CPU overhead, which performs slightly better than the previous approach, but still results in the FPS dropping at a few hundred hex frames, which amounts to a few 100,000 individual hexagons. To render millions, we want to do all of the work on the GPU. By doing so, my laptop could easily handle 3 million hexagons in the demo, with no issues. But my old smartphone could not. In case anyone has an old phone like me, I limited the demo to just 100 rings. Anyways, we can have the GPU do all the work by applying the position offsets and hexagon rotations in a shader. Three.js has 3 shader language or TSL, which compiles to both GLSL for WebGL and WGSL for WebGPU, which I used for my implementation. It's convenient because you import functions from 3/TSL and write your shader logic in JavaScript syntax instead of the more verbose shader languages. Here's what the code looks like. First, we used the grid positions to generate offsets and rotations for each hexagon. Three.js circle geometries stand perpendicular to the ground plane, so I choose to generate grid points for the ground plane and rotate the geometry to lie flat on that plane, with the pointy side facing up instead of the flat one. Next, we generate hexagon meshes using the circle geometry and hexagon outlines by dropping the center vertex to render a line. Then we use TSL, or 3 shader language, to apply the position offsets and quaternion rotation to a line basic material for outlined hexagons and mesh basic material for both solid and wireframe hexagons. Next, we have some conditional logic to set the geometry and material to either line for outlines or mesh for solid and wireframe. And lastly, here's the React logic for rendering our geometry and material in a line or mesh. Connect the various parameters to the controls, and that's the demo, which you can find in the description. But there are 2 more optimizations to make. Comment below if you can guess what they are. Your clue is that we'll address them in Blender. Okay, the first optimization is that this is what our hexagon created with the Three.js circle geometry looks like. It's made up of 6 triangles, but we can create a hexagon shape with just 4, which reduces the number of triangles we need for rendering our scene by 1/3. When we have a quad like this in the center of the hexagon here, it automatically gets converted into 2 triangles at export. So 2 triangles and 1 quad results in 4 triangles. The second optimization is that we don't need to have our GPU apply rotations in the shader. We can export a pre-rotated model and delete the rotation logic from our code. You could actually create a buffer geometry using just the coordinates of the optimized hexagon instead of importing the whole model, but I chose to keep it as a model in case I want to add depth to the tile to make it more 3-dimensional, or make other creative changes without having to update my code. Let me know if you were able to guess, or if you have any other ideas. Now, the grid won't actually be rendered in the final game, but it's very useful to have this set up for debugging player movement and combat. These hex grids are a popular choice for strategy games, but I don't know how common they are in other genres. Let me know if you do. For today's demo, I left the 6 triangle circle geometry, and the updated code with our 4 triangle hex tiles is in the next one and on. Now, before I tell you what the next episode is about, don't forget to subscribe to get my devlogs, and check out the interactive demo linked in the description. And if you'd like to support me further, I'll be launching channel memberships once we have 1,000 subscribers, in addition to a Patreon page available now, which will give you access to the full source code and 3D assets for today's demo, early access to future demos and playtests, my Discord server, and exclusive items in the PvP swordfighting action game I'm building for anyone who backs me all the way to launch. Next episode, I'll be adding 8-directional movement with WASD keyboard controls. See you next time.